Okay, for anybody who missed today's less anybody who missed today's lesson, um, here's a quick summary of it, and I'll go through the same examples that I did in class. Make sure you get to class though. Uh, it's going to be a big help. What we're focusing on before next test. It's a new chapter, but we're just going to focus on these first three sections. Okay. And the first two, I think, will be relatively easy. That third one I know is a difficult lesson. But before we get started into that, what we want to do is just review a little bit. So today's homework assignment was just a review assignment. So let's take a look at the review problems, the examples that I gave in class today. Here is number 1, 2, and 3. And this we just talked about like terms. Like terms have a couple things in common. Number 1, they have to have the exact same variables. Could just be the exact same one, or maybe if they both have 2, they have the same 2. And those variables have to be raised to the same exponent. So that same power. So if we look at the 2 in this first example here, this is a 9x, that's x to the first power. Say 4 times x, that's x to the first power. So it's kind of like counting up how many x's you have. It's exactly like that, in fact. I have 9 x's, but I'm going to add 4 more x's on, so how many do I end up with? Well, I end up with a total of 13 x's. And we aren't solving these, we're just simplifying them. Trying to make something, in this case, that had 2 terms, it simplifies down to a single term. Much easier to look at and deal with. The second example, we have 5x squareds and 6x squareds. Okay, I could highlight the whole thing, but I wanted to point out that that x squared part's the important thing because that's what makes them like terms. If I have 5x squareds and I add on 6 more x squareds, then I have a total of 11x squareds. In this last example in this series, example 3, we've got 4 terms. It looks very, very confusing, but if you break it up, you'll notice this is an x squared term, and so is this. So those two can be added together. The 9x and the 4x, those are both x terms, so those can be added together. So when we add those like terms, the green ones, 5x squareds plus 6x squareds, it's 11x squareds. And the purplish ones, 9x plus 4x, gives me a total of 13 x's. And we stop there. We cannot combine those. This first one is an x squared term, and it cannot be added to an x. Okay? So when we have these like terms, okay, same variable, same exponent, you can add or subtract them from each other. All right? Doesn't matter when we're multiplying. Multiplying is a different rule. But for addition and subtraction, they got to be exactly the same variable with the same exponent. So example 4 here. In example 4, something students are very good with, notice we've got an x plus 4, so we can't add those together, but we're supposed to take that times 2. Okay, so this is what we call a binomial. Bi meaning two terms, and we have to multiply it by 2, and over here we have a binomial. We can't add those or subtract them. They aren't like terms, but we couldn't multiply. Okay, so let's do a little multiplication, and you guys know this is called the distributive property of multiplication over addition. See that addition symbol in there. So we got 2 times x and 2 times 4. Then we distribute this 3. And we go 3 times 6. And 3 times, it's a negative 1 right there. We just never show that 1 in front of it. So it's 3 times negative 1. negative 3x. Let's find some like terms. There we go. An x term, 2x, and an x term, negative 3x. Those are like terms, so 2 take away 3, negative 1x. And we also have like terms here. These are both constants, no variable at all with them. So that's 8 plus 18, 26. So this would be a perfectly acceptable answer, but generally you would see it written this way. We usually don't show a 1 as a factor or as a multiplier out in front because 1 times x is just x. Or in this case, negative 1 times x is just negative x. We can't squish those together. We can't do anything with them. We just leave it like that. We've taken a very complex problem and we've simplified it into something much smaller. All right, next type of problem. So that's our simplifying problems. Then we have some find the volume problems, okay? And what I explained in class is when we want to find the volume, we have to know some formulas. So I'm going to draw a little cube. Let's make sure I can touch him. And this guy right here is 1 centimeter by 1 centimeter by 1 centimeter. He is 1 centimeter, and we call it cubed. Okay, that's how much space he takes up. That's what a volume is, the amount of space you take up. So when we're asked to find the volume of this rectangular prism, which is shown right here, it's just asking how many of these little rectangular cubes can fit inside of this box. If I could fit 10 of them in there, it'd be a total of 10 cubic centimeters. If I could fit 20 in there, it'd be 20 cubic centimeters. Now I'm just showing it right now on the ground level, but remember, after I filled up this bottom with all these cubic centimeters, I could go up a level and I'd have to fill it again until I finished off filling up the top. And so you could actually fill this with all these cubes to figure out how many, or you could use the formula that we use. For rectangular prisms, rectangular prisms, we just have to use length times width times height. Now, it usually isn't written in this form. Usually we just write volume equals length times width times height, with L for length, width with W, and H standing for height. Now, a lot of students asked today, when they started it, they asked which one of these is the length, which one's the width, and which one's the height. And the answer is it doesn't really matter. Okay, because of the commutative property of multiplication, you could multiply these in any order you wanted to. So you could do 10 times 4 times 5. You could do 4 times 5 times 10. You could use 5 times 10 times 4. It's not going to matter. All of these, when you multiply them, come out to 200. Okay, now we do want to put units on this. Because each dimension was in centimeters, we've essentially multiplied centimeters here, 10 centimeters, times 4 centimeters. Well, centimeters times centimeters, that's like a centimeter squared, times another centimeter. And so it's 200 centimeters cubed. Okay, and what that means is that this little box, this 1 cubic centimeter, you could fit 200 of them inside of this rectangular prism to fill it up. And that is a measure of volume. The last example we have is a little more difficult. This time we have a sphere. So think of this as a basketball right over here. Okay, it's about, it says 5 inches for the radius. So the radius, you can see it marked with an R here, is 5 inches. So it's about the size of a basketball. All right, and in this case, again, we're trying to figure out how many, in this case, square inches fit inside this, or cubic inches. My apology. Okay, so how many of these could you fit in there? And it's a much tougher problem because the squares, these cubic inches, don't fit inside this round value. So it's kind of tough. It just grouped me for some reason. But fortunately, we have a wonderful formula, which is given right here, to find the volume of any perfect sphere like this. And volume is just 4/3 times pi. Now remember, pi is an abbreviation for this irrational number that goes on and on forever. It's fine for us to approximate it as 3.14. And then times the radius. Radius is 5 cubed. Okay, so as we work this problem, there's a number of ways to work it, but let's deal with the exponent first. 4/3 times 3.14 times 5 cubed. 5 cubed is 125. Then I just have to figure out what 4/3 times 3.14 times 125 is, and I'll do it in steps here. I have to get out my calculator. When we multiply fractions, notice I put it over 1, so I have numerators there. I'm going to multiply my numerators. See if I can find my calculator. There it is. 4 times 3.14 times 125. Numerator is 1,570. Denominator, just 3 times 1, which is 3, times 1, which is also 3. So 1570 divided by 3, I could fit 523.3 approximately of these, in this case, cubic inches. Why cubic inches? Because the 5 right there, it was 5 inches, and so I cubed 5 inches, and so I have to cube the inch part as well, which gives me 523.3 of these little cubes would fit inside that sphere. All right, your homework is also posted. Looks like this. You can see the first 6 problems are simplified. That was like the first 4 examples. And then the last 3 problems, 7, 8, no, last 4, those are volume problems. Don't forget number 10 up here, okay? So we got 4 of those. Ooh, ignore the assignment name down at the bottom. All right, that should get you guys through this first lesson. Please get it done promptly. Thank you.